first talk is about matrix multiplication, and Virginia and Josh are jointly going to present the talk. So I'll let Virginia start.
Thanks, Shubhangi. Thanks for inviting me. So I have a bit of a cold, and I think, or something, so I might be coughing. I'll try to refrain from coughing, but Josh has been gracious enough as the second expert on this topic to give the second half of the talk. So let's begin. So this is a talk about one of my favorite problems, matrix multiplication. For a long time, we tried to improve on the running time for this problem, and unfortunately, there seem to be diminishing returns, and we try to understand why this is the case, and this is what this talk is about. Okay, so let me introduce the problem to you, although I'm sure all of you know what it is about. So you have two n by n matrices, and you want to compute their product. In particular, this is a bilinear form, and you're just evaluating it over some input. And here we'll assume the arithmetic circuit model. Let's assume all the entries of the matrices are, let's say, complex numbers. So in general, there's some field, and we count the number of operations we take to compute this bilinear form, and the operations are additions, multiplications, divisions over the field. Okay, and we'll assume each of these operations takes constant time, and we worry about asymptotics. So clearly, the naive algorithm just follows the definition, and you can definitely compute the product of two n by n matrices in n cubed time. And a big breakthrough was by Strassen, who showed that actually you can do it faster in n to the 2.81 time. And then there was a lot of improvements, which I'll talk a little bit about in a little while. And then this culminated in the current best running time, which is something like n to the 2.3729. Okay, and probably can improve a little bit more somewhere in the decimal places over here if you work a little harder, but we have other things to do. So, so we can define omega, which is the matrix multiplication exponent. We'll define it a little bit more formally in a little bit. And for now, just say omega is the smallest real number for which you can multiply n by n matrices in n to the omega plus little o of one time. And of course, from here, we get that omega is at most this. Okay, so the big open question is omega equal to 2? In other words, can we multiply two matrices in roughly linear time in their input? Why should we even believe that? Well, we don't have any lower bounds that tell us the otherwise. But why should we believe it should be omega equals 2? Maybe, throughout the last decade that I've been thinking about this problem, now I think it's omega is bigger than 2. So, what is this? Whatever. All right. So I will give you a very high-level overview of matrix multiplication algorithms to date, and then we'll kind of narrow in on this view, and then we'll generalize it. Sorry. I don't know what's going on there. Just okay. So there's two components to any matrix multiplication algorithm nowadays. First, you come up with some identity, which tells you that some trilinear form, which I'll define in a bit, can be computed very efficiently. And then there's a second component, which is a method to embed our favorite form, matrix multiplication, into this efficiently computable one in some way. And we'll narrow in on what I mean over here. This is a very high-level view. Okay. And then if you apply this method to this trilinear form that you understand, you get the matrix multiplication algorithm. So there's roughly two approaches which can yield the current best bound on matrix multiplication algorithms. The first one is the Strassen / Coppersmith Winograd approach, where M is the so-called laser method, which I'll briefly explain later on. And this method works very well on some very structured types of tensors. And the current best record from omega is given by this Coppersmith Winograd tensor, which I'll show you later on. The second type of approach, which can give roughly the same bounds, is the so-called group theoretic approach, which was started by Cohn and Ullmans. And the method is the group theoretic method. And the tensor that one uses is basically you take some very structured group and you define the structural tensor of its group algebra, and this is the tensor you use, and there's various methods to come up with the identity for these tensors, and then the method is very nice and beautiful. Okay. So a very rough view of what we have. So there's these two methods that yield the current best bounds on omega. And now what we do, the first thing we do in our work is we generalize them. So first, we define several methods over here that all subsume both of these. So the first one we arbitrarily call the solar method, because Strassen called this pretty much arbitrarily the laser method, so we reserve the right to continue the tradition. So, okay, so this is the solar method, you reach the sun. Then you have the galactic method, you go to some other galaxy. And the universal method is basically the dream approach that subsumes all of these. And I want to point out that while these are very nice methods and we know how to use them to analyze particular tensors, these ones, the generalizations, we don't have any way right now to get the best implementation of these methods. They're just dream methods out there. Okay, now I'll define them in a second. Okay, so there was some prior work on limitations of these methods over here. For the laser method, there was work by Ambainis, Filmus, and Legal, who showed that you cannot prove that omega equals 2 if you restrict yourself to the Coppersmith-Winograd tensor, which is the current best record holder, and you use exactly the implementation of the laser method that has been used in the work so far. So in particular, there's a particular constant is much bigger than 2 for which you cannot go beyond with these methods.
So is that a constant that goes to 2 as q goes to infinity?
So here, not really. Like the best is like at 5, and there's the best lower bound is for q equals 5, which is also the current best upper bound. But still, it's quite restricted to these particular methods of analyzing tensors. Yeah.
Do we know that laser method and group theoretic method are different?
So they analyze different tensors. So ultimately, these approaches, all of these approaches, they are only for analyzing a fixed type of tensor that you're working with. And if you change the tensor, there'll be the same method. Like I can always apply all of these methods to the matrix multiplication tensor, apply. And so they'll be the same. But because they're analyzing different methods, they are different. They are subsumed by this one, as we'll see later.
But you can simulate the laser method using the group theoretic method, supposedly.
Sorry?
Some people claim that you can simulate the laser method using the group theoretic.
Okay, so he said that some people claim you can simulate the laser method using the group theoretic method. That is kind of true. So in a sense, like the Coppersmith-Winograd tensor, you can find a related tensor that gives the same omega, and you can embed it in a group theory tensor, and yes, you can simulate it, but that doesn't mean, you're analyzing this tensor exactly and so on. So in some sense, it could be true, but it's not formally true.
So that's roughly the reason why they give the same bound?
So the reason why they give the same bound is because you can, exactly why, because you can change this to a slightly related tensor, embed it into a group tensor, use the mechanisms here. So, all right, so now, so we had this, but it was restricted to these types of methods. Now, over here, it's also known that if you pick any fixed group and you apply the group theoretic method, you also not give 2. Now, this was by Blasiak, Kohn, Church, Grochow, Ummans, Selwyn, and one more person, and I wrote it down. I'm sorry. Nasland. That's it.
So what do you mean by fixed groups?
This, I'm going to elaborate on this. So now, you could take some group and analyze it and its tensor powers, okay? And then you will not get omega equals 2. But you could have groups that are parameterized by something like the symmetric group on n elements, right? And then this limitation would not apply to like the method where you analyze the symmetric group, how well it would do for matrix multiplication, and then you pick the best n. So this will not, you might still get omega equals 2 there. So fixed group just means you pick a group that's not parameterized by anything and potentially just use its tensor powers, but not some parameterized thing, family of groups that you could analyze. So it's a little limited, but still says something, a limitation on this. Okay, so what do? So we take this vast generalization of these methods, and we say that even this method applied to the Coppersmith-Winograd tensor for any q, I will not give omega equals 2. In particular, there's a fixed constant, something like 2.001 or something, that you can go below no matter what q you get, even if you take q goes to infinity. And also the same sort of fixed group thing here also applies to this method. So you cannot get omega equals 2 for fixed groups and their tensor powers.
So,
Yes.
so the very high level, I'm saying that there are two things. So there is a tensor or a group, and then there is a way to analyze the tensor.
That's right. We'll get into this now. This is a very high level of what's going on now, and I'm going to narrow in and define a bunch of stuff.
You're not yet telling us that you can analyze any possible tensor, just the ones that people consider.
That's right. Yes. So we yes. So let me get into it. So I'll get into the details now.
Just a high-level question.
Yes.
Galactic method is a general method, and you cannot use it with this tensor to get omega.
Yes.
You can use it with other tensors.
You could, in particular, with the matrix multiplication tensor. Yes. Yes. Absolutely.
And also maybe the universal method, whatever it is, can be used with this tensor.
Absolutely. So the universal method could be used with these tensors, except that now we have some proofs, maybe, that show that this also is not true. But Josh is coming up with more and more techniques and verifying them. So let's see. Okay. Sorry. Okay. So let me just give some basic definitions so I can give you more of an idea of what we're saying here. Okay. So in this talk, we'll define tensors as the following trilinear form. So you have these three sets of variables, x1 to xn, y1 to yn, and z1 to zp. And they're formal variables, and a tensor will define as a trilinear form where you get these coefficients ti, j, k that multiply xi, yj, zk. All right, you can think of these ti, j, k's as coming from an underlying field like the complex numbers. Okay, now that we have this, we can define a rank 1 tensor as a product of linear combinations of the x variables, y variables, and z variables. So this is a rank 1 tensor. And now, just like with matrices, the rank of a tensor is the minimum number of rank 1 tensors whose sum equals the tensor. All right, if you're not comfortable with trilinear forms, you can think of the usual definition of a tensor as belonging to Cn, tensor Cm, tensor Cp, or alternatively for the rank 1 tensors, they're just A, tensor B, tensor C. All right, so what is a matrix multiplication tensor? Well, it's written like this. The m by m matrix multiplication is mmm, and it's the sum over xij, yjk, zik. Basically has a 1 only in front of these products, and as an intuition, the coefficient of the zik entry is exactly the product of the ith row and the jth column of the matrices. So this is why it defines matrix multiplication. All right, and something you've seen before when teaching or learning about Strasson's algorithm is that if we know that the rank of the m by m matrix multiplication tensor is, let's say, k, like for 2 by 2 it's 7, then we can get a recursive algorithm for n by n matrix multiplication just by blocking. So you take your n by n matrices, you block them into m by m blocks, each of size n over m by n over m. Then you use your identity that comes from the rank expression over here to form these linear combinations of the blocks. And luckily for us, linear combinations just involve summing matrices, which is linear time and the sum of the number of entries. And then you perform products of these blocks using the recursive approach, and then you use the rank expression again to assemble the final product by getting them. So then you get this recursive running time. T of n is k times T of n over m plus order n squared. So as long as k is smaller than n cubed, you get something subcubic. All right, so then you get that from a rank expression, you get an omega upper bound of log base m of k. All right, so this is just the basics. So now we can go, this is just a recap. And then we can define omega as just the lim over m of log m of the rank of m by m matrix multiplication. And you can say matrix multiplication takes n to the omega time. All right, so now this motivates the goal of getting upper bounds for matrix multiplication tensors for fixed dimensions. So for 2 by 2, we know the rank is at most 7. In fact, it's exactly 7. And so you get Strasson's bound. Then for 70 by 70, Pan gave this monstrous upper bound, which still gives something better than Strasson. And you can try even more and more. However, these matrices get unwieldy. It's very difficult to bound their rank. And in fact, even for 3 by 3 matrix multiplication, we don't know the best rank bound. So this motivates the next approach, which means instead of just fixing some fixed size matrix multiplication tensor, you pick some other tensor that we want to understand. So here's the next approach. We take,
Part of the difficulty is the fact that tensor rank is NP-hard. I mean, if it was just matrix rank, then we can probably do it for higher...
I mean, it's NP-hard, but of course these are very structured tensors. It's not like we're working with very hard ones, but it's still very difficult to analyze it. And if you, even when you define a search space and you get rid of all the symmetries, even for 3 by 3, the search space is enormous. We don't have a good way to analyze it. Anyway, it's tough. Okay, so what we do instead is we take a tensor that may not be a matrix multiplication tensor, and some tensor for whose rank we really know. For example, this is one reason why the group tensors are so nice, because we can get their ranks very easily. So they follow from group theory, from representation theory in particular. So, and then after we have a tensor whose rank is very nice and small, then we try to show that T contains a large matrix multiplication tensor. What does this contain? Well, if this containment does not increase the rank of the underlying tensor, then you would get that the rank of m by m matrix multiplication is bounded by the rank of the tensor, and then you can apply the previous approach, just as before. Of course, this has this issue that now we have to understand the ranks of these still big tensors, and so it's still not as nice. Because of this, we instead work with tensor products, in particular the Kronecker product of tensors. What is this? So you have, let's say I have two tensors A and B. They're trilinear forms over variables x, y, z, and x prime, y prime, z prime. And we can define a new tensor, which is their tensor product, a Kronecker product, which is just, you take, okay, so you basically, you take all the triples ijk and I prime, j prime, k prime, and you take aijk times bi prime, j prime, k prime, and then the variables are just pairs of the original variables. And this sum is over all pairs. And you can just think of like A and B as polynomials, you multiply them, and then you replace their variable sets with new variables, like that corresponds to pairs. So this is the Kronecker product. What's nice about this Kronecker products, two things: the product of A by A matrix multiplication and B by P is exactly AB, the AB by AB matrix multiplication. This is just follows by blocking. And also, we have this nice property that we really like, is that tensor rank is submultiplicative under this product. So it's nice. So now it gives us this new approach. So now instead of just multiplying, you can take powers of a tensor. What's a power? Well, you just multiply the tensor by itself, let's say n times, and that gives you the nth power. This gives you a tensor over whose variables are just indexed by sequences of the original indices. So you have a bunch of variables, and also the rank of the nth power is at most the nth power of the rank. But actually what's nice is that actually the rank of the tensor power can drop significantly in the exponent. For example, if you take 2 by 2 matrix multiplication, we know its rank is 7. However, if we take the nth power, it's much smaller than 7 to the n, because, as we know, omega is much less than 2.81. So we have this nice thing, and this motivates defining the asymptotic rank of a tensor. So the asymptotic rank is you take the nth power, take the rank of the nth power of the tensor, you take the nth root. And now look at how this grows. You know that it's at most the rank of the original tensor, but it can be much smaller. And in fact, we can use this, the asymptotic rank in place of the rank in our approach. And it will give you better bounds. So now, again, as I said, you can get bounds on omega using the asymptotic rank instead of rank. So now we can do this. So the following refinement of the approach. You start with a tensor T. That's not necessarily matrix multiplication. You show that it has small asymptotic rank in some way. Then you take some huge tensor power of it and analyze it with some nice techniques, and you show that this tensor power contains some large matrix multiplication tensor where the dimension of the tensor depends on n, and you can take n to infinity and do stuff, and then you get some very nice bounds. And now let's talk about what containment means. So containment, we want that if A contains B, then the asymptotic rank of A is at least the asymptotic rank of B. Okay? And as from our previous slide, we know that if this holds, then and the tensor power contains this matrix multiplication tensor, then we're actually bounding the asymptotic rank of m by m matrix multiplication, and we bound omega. Okay, and now we get to this containment notion. We define 3 different options of increasing strengths. So the first one, which I'll define on the next slide, is zeroing out. The second one is we call monomial degeneration. The third one is just degeneration, arbitrary degeneration. And each is subsumed by the one below it. Yes?
If we bound the asymptotic rank of the matrix multiplication tensor, does it also give us a better algorithm?
Yes. Yeah, I mean, this is actually this is what we want. We want to bound the asymptotic rank to get to omega. Okay, so, all right. I want to, as an aside, I want to actually say something that instead of containing a single matrix multiplication tensor by a theorem of Schoenhage, we know that actually it's okay for the tensor power to contain a bunch of matrix multiplication tensors that do not share any variables. So, and this will also give you a bound on omega via this asymptotic rank inequality by Schoenhage, but and then it gives you this more general approach, which is you show that T has small asymptotic rank, and then you show that the tensor power contains many big independent matrix multiplication tensors, where many and big depend on n in the tensor. Okay, but for the purposes of this talk, so I don't keep writing direct sums, I'm going to ignore this, but keep in mind that everything I say actually applies there. Okay, so forget about this, and now let's define zeroing out. So let's say I take a tensor A and a tensor B, and I'll define what it means that B is a zeroing out of A. So B is a zeroing out of A if you can get B by removing all occurrences of some variables in A. So you just set them to 0. So for example, let's say I take this tensor over here, and I can get the tensor B by setting the variable y1 to 0. And this will remove this triple and this triple. So that's what zeroing out means. So I get only these. And note, so when you do this, you will get some subtensor of the previous one. but you cannot get any one that you want. Yeah.
So in terms of like a three-dimensional representation of the tensor, this is the same as like removing one plane?
Yes. Yeah, you just remove some plane. So you can pick any sets of variables and remove them. So you remove a bunch of planes, and you'll get a new tensor. So I want to point out that if you take the first three sums over here, you cannot zero out A to C, because this term over here shares a variable with every single one of these. So you cannot zero this thing out without zeroing out one of these. And because of this, we will see soon that if we take the next version of containment, monomial degeneration, you can get to C. So actually, monomial degenerations are strictly stronger than zeroing out. Okay, so now another thing that's very, very easy to see is that if A zeroes out to B, then the rank of A is at least the rank of B, which is what we wanted. Basically, you just take the original rank expression and get rid of the variables that you don't need. Okay, so this is good. This is the simplest thing, and in fact, this is what all our approaches do. They actually do zeroing out. Okay, next. I'll define degeneration now.
So actually, just going back to that point, so you're saying the group theoretic methods as well as the laser method was doing this?
Absolutely, both the group theoretic method and the Coppersmith Winograd method, they both do zeroing out. They do not go to the further. Yes?
Maybe a silly question, but is it true that if the rank of A is bigger than B, then the asymptotic ranks also have the same property?
So in this case, it's true.
Okay.
I can also put asymptotic here.
Okay.
Yeah, it's true.
Just because like the tensor power of a zeroed out matrix is the zeroed out matrix of the tensor power?
Yes, yeah. Yeah, yes. So, okay. So, now the degeneration is a little bit messier. So let me define it. Imagine we have two tensors over different sets of variables. A is over x, y, z, and B is over x prime, y prime, z prime. Sorry. So to get from A to B, what we do is we take the variables of A and replace them with linear combinations of the variables of B, where the coefficients in the linear combinations are polynomials and some indeterminate epsilon. So in other words, you can take matrices P, Q, and R that take the variables, K basically is a K prime by K matrix, so that they take the x, y, z variables to x prime, y prime, z variables, and the entries of these matrices are polynomials over epsilon. And then you can write this thing. So applying these transformations to the tensor A will give you some expressions whose coefficients are polynomials in epsilon. So if you take the terms that have the smallest powers of epsilon as coefficients, and they give you exactly B, then B is a degeneration of A. This big O thing gets rid of terms that are multiplied by powers of epsilon that are bigger than the smallest term. And I'll give you an example in a second. So this is a degeneration. Yes?
It's equivalent to looking at border rank, right?
So border rank you use degeneration to get border rank. Yeah, you degenerate to an independent tensor. The other way. The dependent tensor degenerates to your thing. Okay. All right. So intuitively, what happens here is if you take, you divide this transformation you got here by 1 over epsilon to the h, where this is the smallest power, and you take epsilon to go to infinity, all these terms will go away, and you'll get exactly B. So you will have a sequence of tensors that converge to B. That's what you'll get. And by theorem of Baibini, if A degenerates to B, then the asymptotic rank of A is at least the asymptotic rank of B. And this comes to Avi's question. That's where it was a theorem about border rank.
So Virginia, I'm a little puzzled now. So you're saying that this is a more powerful operation than zeroing out.
Yes.
But I thought many previous results used to be about the border rank rather than about the rank itself.
Yeah, so the thing is that border, so I'm not defining border rank, but if you take tensor powers, border rank is like rank.
Same as rank.
So it doesn't actually matter. And for us, we're analyzing big tensor powers, and actually everybody uses Schoenhagen's theorem, and Schoenhagen's theorem is about zeroing out. So we don't actually use this full power here.
And the second thing is this can dominate zeroing out?
Yes, it can.
Okay.
So, I mean, if you just put epsilon in front of the variables that you want to zero out, I think
that's what I'm going to say now. Okay.
Oh, okay.
Yes, so let me do this. So first of all, let me define monomial degeneration. In monomial degeneration, it's a degeneration in which the entries of PQ and R are just monomials over epsilon. So they're not arbitrary polynomials. Okay, like 1 over 7 times epsilon to the 10. Yeah, it's monomials. So let me give you an example of monomial degeneration, and I'll get back to what Russell said. So monomial degeneration example, very simple example. We take our original tensor and now degenerate it to this tensor C where zeroing out was not possible. So what we do is we multiply x0, y1, and z1 by epsilon. And what happens then is you get everything except for x1, y1, z1 gets a power of epsilon, that's just the first power. But this one gets 2, it gets epsilon squared because it contains both y1 and z1. And because of this is exactly this tensor C, and so we get that A actually monomially degenerates to C. And you can get some examples where you can degenerate, but you cannot monomial degenerate, and you cannot zero. So these are increasing powers of embeddings of tensors that do not increase the rank. Okay, so now back to Russell's question. If you can zero out to C, you can also monomial degenerate because everything that you zero out, you just multiply by epsilon and you get this. You'll get exactly what you want. Basically, all the zeroed out variables will get some power of epsilon in front of them, and all the other terms that don't have zeroed out variables will have just epsilon to the 0. Okay, so good, thank you. And now, we can say, now the known approaches are like this. You take some tensor that you really understand, its asymptotic rank is tiny. You take a tensor power, you degenerate to some matrix multiplication tensor, and then you combine these two methods to get the bound on omega. And the degeneration you use can vary. It can be universal method, galactic, and solar method. What tensors have been used? Strassen used just the 2x2 matrix multiplication tensor itself. And then there were many, many follow-ups after that. And then in 1986, Strassen used a tensor that is not a matrix multiplication tensor, not a sum, not a disjoint sum of them. And this is some funny-looking tensor here. Each of these is a matrix multiplication tensor, but they share variables, so it's pretty messy. And this is where he defined the laser method. And then Coppersmith, Winograd, and us, and many people here, we use this tensor. It's very structured. So, oops. Yeah.
If you take just identity tensor, then the question of tensor rank is just if this identity tensor can be degenerated to the matrix multiplication, right?
Yes, that's a definition of border rank.
Even frank. So the question like of general generalization is like equivalent to the question of tensor rank.
Which one? Up here, this, yes. Yeah. That's why it's universal. Okay, so, all right. So I will just, I'll take 2 minutes and then you can take over. So the first method, the laser method, roughly what it does, it takes these tensors that are very nice in the sense that they can be partitioned into things that look like matrix multiplication tensor. For example, the Coppersmith-Winograd tensor is nice because if you take this part, this part, this part, and this, and this, they're all matrix multiplication tensors. In particular, each of these is either 1, 1q, or 1q1, or q1, 1. That's what the star means. And each of these is a 1, 1, 1. And what the method does is, when you take tensor powers of this tensor here, you just cleverly zero things out, so you get tensor powers of these little tensors, which are all matrix multiplications, and you do some stuff to make them independent, and then you get exactly what you want. You'll get that you can use Schoenhagen's theorem, and you can use all the techniques that we have. But the whole point is that all of the methods, all what this method does is just use some basic combinatorics. Sets excluding three-term arithmetic progressions and related stuff to analyze what happens to this tensor when you take tensor powers. The group theoretic method. It was introduced by Kohn and Ullmans, and it works very nice for these tensors, the structural tensors of the group algebras of a group G, and they're defined like this. You take the sum over all pairs of group elements of xa, xa, yb, z, a times b. So you have a 1 only when the index of z is a times b here. All right. So here's a simple example, very nice structured tensor for z2. And the nice thing is that the rank, border rank, asymptotic rank, is very easily analyzed. It's upper bounded by the character degrees of the group algebras. So you can get a very nice expression on the asymptotic rank. And
what do you mean by character degrees?
So if you can use representation theory to take the tensor here and represent as like block tensors of matrix multiplication, and then if you take the character degrees, you get the rank is upper bound by the sum of the degree to the omega.
By character degrees, you mean the dimension of the representation?
Yes.
Oh, that is what I was.
Oh, sorry. Yes. Yeah. All right. So, okay. So then there's
What
this.
is the bound you said?
Oh, if your character degrees are d1 up to whatever dk, it will be upper bounded by the sum over I of d sub I to the omega.
Oh, I see.
So it's a nice bound. So then, so then this part is relatively nice because of the nice structure of these tensors, and then Kohn and Ullmans and follow-up works defined some nice properties of groups, such as the triple product property and simultaneous triple product property and so on, to give you a zeroing out of the tensor or its tensor powers to matrix multiplication tensors, and that's the second part of the approach. But it's again only zeroing out. All right, this part uses representation theory, and this one just group theory. All right, so now it's time for Josh to take over, and thanks for me.
Give me the mic.
I think that works. Yeah. Okay. Hello. So I guess just to recap what Virginia was saying, these two known approaches that we have for getting the best known bounds on omega, they focus on particular nice tensors. Like the laser method works for tensors which have some structure, like the Coppersmith Winograd tensor. The group theoretic method works for these group algebra tensors. And they both give ways to show that powers of your tensor can zero out into big matrix multiplication tensors. But it's possible that bigger zero matrix multiplication tensors exist inside these tensors that these methods don't find. And for instance, I think we even believe that they almost certainly do. Like the improvements from Coppersmith Winograd's paper to the more recent results can be viewed as like slightly improving the laser method to find slightly bigger matrix mult tensors. And then, not to mention, if you move, say, to monomial degenerations, maybe you can find even bigger matrix multiplication tensors. So then our results are limitations on how big matrix multiplication tensors you can actually find in powers of these tensors. So our first main result, Virginia mentioned earlier, is that there's a universal constant C bigger than 2, such that you can't get a better bound on omega than C using the galactic method, these monomial degenerations applied to Coppersmith Winograd tensors for any Q. And then similarly, we show for each finite group G, there's a constant bigger than 2 such that you can't get better than that constant using the galactic method applied to the group tensor. Yeah, so just a couple of notes about these things. For the first theorem about the Coppersmith Winograd tensor, I'm about to show you pretty much the entire proof. Where you'll see it actually only uses like a really small amount of the structure of the Coppersmith Winograd tensor, so it applies to a lot of similar looking tensors. And I think probably like any tensor where the laser method could apply to it, you can say something using these types of techniques. And then for theorem 2, so Virginia mentioned this, but you get a different constant bigger than 2 for each group. So it actually doesn't rule out trying to get omega equals 2 by finding a sequence of groups where this constant approaches 2 and analyzing this sequence of groups in the limit. And this kind of limitation is pretty well understood among the people who studied the group theoretic method, I guess. And in fact, there's this paper from last year by Will Sawin which actually also implies our theorem 2 result. And in fact, if I understand correctly, I think it even implies it for the universal method for fixed groups can't get, so no fixed group can get omega equals 2 using the universal method. But still, we don't know how to rule out sequences of groups.
So galactic method is equivalent to monomial degeneration.
Yeah.
Okay.
Yeah. Galactic method means monomial degenerations. Yeah.
Does the optimum Q change with the method? Like the Q equals 5, like does it change with the laser? It's 5.
Actually the Q for which our lower bound is worse is like Q equals 25 actually. So it's a bit bigger than the one for which our upper bound is best. Yeah, but I think that's might be just an artifact of our analysis rather than like what the actual best or worst Q is. Okay. So the picture really looks like this, that we prove a lower bound against the galactic method for all of these different tensors. Okay, and in the rest of the time, I'm going to show you pretty much the entirety of our proof of the lower bound for the Coppersmith Winograd tensor. I think it's relatively simple, so I should be able to explain almost everything about it. Okay, so our proof technique is to go through something called an independent tensor or a diagonal tensor. So this is just the qth diagonal tensor. It's written with these triangle braces q. Is just a tensor with q terms that share no variables with each other. So it's like the analog of the identity matrix. And we're going to be really interested in degenerations from tensors to independent tensors. So for a tensor b, I'll let I of b be the biggest number q, such that there's a degeneration from b to an independent tensor of size q. And similarly to how we had like rank and asymptotic rank, we want to look at like asymptotic I. So I'll let I tilde, which I'll call the asymptotic subrank of b, is the max or the lim sup over all n of I of the power to the power of 1 over n. And yeah, in fact, Strawson actually studied this asymptotic subrank notation in a line of work like 20 or 30 years ago. Okay, and similar to how we had these 3 different methods for whether you're using degenerations or monomial degenerations or zeroing outs, we're similarly going to have variance on this I for the 3 different methods. So I'll write I sub md for the biggest q that your tensor can monomial degenerate into. And then the asymptotic version of this, I'll call it the galactic subrank of the tensor. And similarly, I sub zo, the biggest tensor you can zero out into, and I tilde is the solar subrank of the tensor. In our paper, we actually call this the independence number of the tensor. But I think solar subrank, or asymptotic solar subrank might be a better name for it.
You could have called this monomial degeneration subrank and zeroing out subrank, which would capture what you're doing.
Yeah. I think galactic subrank sounds cooler. I don't know.
If you want to know what it means, then it's
That's true. Okay. So why are we interested in this? Well, first some nice properties of it. So it's not hard to see the zeroing out subranks less than or equal to the monomial degeneration subrank less than or equal to the subrank, just because these different notions are stronger and stronger. It's also not so hard to see that the asymptotic subranks less than or equal to the asymptotic rank, just because a degeneration to an independent tensor would give an asymptotic rank upper bound for the independent tensor, and the tensor with q terms actually has to have asymptotic rank q. Okay.
The last is the quality, right?
Sorry?
The last one is the quality.
leftmost one? Or which?
Right. No.
Oh, no, it's not. It's yeah, it's not very well understood, but as far as we know, it's not equality in general.
Examples where they are different.
Yeah, that's right. Yeah, we know examples where they're different. Yes, they're between the rightmost ones, yes.
RB can be as large as...
So actually, in our paper, we show that the leftmost ones are equal to each other. The zeroing out subrank is equal to the monomial degeneration subrank. And if you've seen like Binney's proof about why border rank suffices for matrix multiplication, the proof of this is really similar to that. Okay, and one other like simple observation is that if B is over the x variables, y variables, and z variables, then the monomial degeneration subrank of B is at most the minimum of the 3 sizes of the sets of variables. And this is just because monomial degeneration always goes from your tensor to a subset of the terms. And if you're getting independent terms at the end, you need at least 1 variable for each of those terms. Okay, so why are we interested in this? Well, there's a really nice result that Strawson actually proved in the 80s that if you rewrite it in our notation, says that the matrix multiplication tensor has its monomial degeneration subrank is as big as possible. So remember the m by m matrix mult tensor, it has m squared x variables, m squared y variables, and m squared z variables. And in fact, its asymptotic galactic subrank, asymptotic monomial degeneration subrank is equal to m squared. So if you have any tensor T, and you're using it to get a bound on omega by monomial degenerating it into a matrix mult tensor, then you can compose this with Strawson's monomial degeneration to get a lower bound on the asymptotic galactic subrank of the tensor T itself. And in particular, if you wanted to use this monomial degeneration from T to the matrix mult tensor to prove omega equals 2, then you would also need it to be the case that the asymptotic rank of T is equal to m squared. So you would need these two things to be equal to each other. And if you're working with like a tensor which is not degenerate in some way, so the asymptotic rank is at least the number of variables, then this means if T is a tensor over k different x, y, and z variables, then it can yield omega equals 2 only if this monomial degeneration I tilde is equal to k. And the more less than k it is, the better a bound away from 2 you can prove on what omega you can yield using it. And so in order to prove our lower bounds on omega that you can yield, we're going to show upper bounds on this I tilde of different tensors. And if you can show it's less than the number of variables, that means you get a lower bound on the omega you can get with it. Okay, so let me show you a sketch of how we do that. And the main idea is a nice lemma we prove that's about assigning a probability distribution to the terms of a tensor. So here it is. So what we show is that if T is a tensor, it has k different variables of each type, and its monomial degeneration I tilde is equal to k, then there's a probability distribution on its terms. So a way to assign a probability to each term so that they sum to 1. And such that for each fixed variable, the sum of the probabilities assigned to the terms containing that variable is 1 in k. So there's a way to assign a probability to each term so that each variable is assigned 1 in k of the probability mass. So let me give you, I'm not going to give you the whole proof of this, but let me give you some intuition for why it might be true. So if we were just looking at I instead of I tilde, so you take your tensor and monomial degenerate to an independent tensor of size k, then well, this is just a subset of the terms, so we could assign probability 1 in k to those terms and 0 to everything else, and it would have this property. And then more generally, when you take big tensor powers, you do a similar thing where these probabilities are kind of like, it's the fraction of the time that you pick that term in your like n tuples of terms of the original tensor. That's the intuition for this.
Is this like a fractional independence number?
Sorry?
Is this like a fractional independence number?
Yeah, I think it's very similar to that. Yeah, in fact, maybe, I'm not sure off the top of my head, but maybe it's the same even. And then, yeah, from here, it's actually really easy to see that the Coppersmith Winograd tensor cannot have a probability distribution like this. so I'll call this P of xi, just the sum of the probabilities assigned to variable xi. So here's the Coppersmith Winograd tensor again. It has q plus 2 of each type of variable. And I'm only going to need to look at these last two terms to show that it can't have this distribution. So if we look at this second to last term here, it's the only term in the tensor that has yq plus 1 in it. So that means we have to assign it probability 1 in q plus 2. And similarly, this last term, it's the only term in the whole tensor that has zq plus 1 in it. We have to assign it probability 1 in q plus 2. And this is already a problem because both those terms have x0 in it. So we've already assigned too much probability mass to x0. It's very simple to see you can't have this type of probability distribution.
So what did you care about in the second of those conditions? Is that an equality or a less than equals or a?
Oh yeah, So like what it actually ends up being is if you look at the L1 distance from the closest you can get to the uniform distribution, to actual uniform distribution, and then the bound on omega you get is just a function of that distance. But as long as you can bound it away from the uniform, that means for this tensor you can't get to. Okay. So if you're paying attention, like I said, I was going to show there's a universal constant independent of 2, but actually this bound I just showed, it holds for all q, but it sort of gets worse and worse as q gets larger. Like this only bounds the L1 distance a little bit as q gets quite large. And I mean, there's some ways to alter that argument, but I'm now going to show you a second, maybe even simpler argument that it only kicks in for large enough q, but it gets better and better at q as q gets larger. And then the min over all q of the max of these two bounds is going to give our constant c that I promised you. Okay, so here it is. We're going to use one other property of the Coppersmith Winograd tensor, that we can partition up its terms in this way. We can partition up its terms into 3 parts, where the first part only has one x variable, the second part only has one y variable, and the third part only has one z variable. So in other words, we're using the fact that each term of the Coppersmith Winograd tensor either has at least one of x0, y0, or z0 in it. Okay? And in fact, it's not even going to matter what these are, so I'm just going to call this x is some tensor with one x variable, and y, and z. So we're going to use the fact that the Coppersmith Winograd tensor can be partitioned into these 3 parts. Okay, so what will we do with this? So here it is. It can be partitioned into these 3 parts. Each term is in exactly one of them. So when you look at the nth power, we can also look at partition it into like which part the term came from in each of the n components. So it's a sum over choosing like the x, y, or z part for each of the n coordinates of the tensor product of those parts. And this is again a partitioning of the terms of the nth power of the tensor. So let's look at just one of these terms in the sum, one of these summands. So for any given one, we know that we made one of the choices either x, y, or z at least a third of the times. So let's say without loss of generality, at least a third of the t sub i's are equal to x. That means the tensor t1 times dot dot times tn has at most q plus 2 to the 2/3 n different x variables. Like in one third of the times, we're multiplying by a tensor that only has one x variable. And the rest of the times, we're multiplying by tensors that have at most q plus 2 x variables. So in total, we only have q plus 2 to the 2/3 n x variables. And in particular, since monomial degenerations can't increase the number of variables, that means I sub md of this tensor, the independence of the number of this tensor, is at most that number of x variables. It's at most q plus 2 to the 2/3 n. Okay, so our tensor, it's a disjoint sum of these different tensors. And in particular, that means that I of the tensor is less than or equal to the sum of I of those different components. This is just because if you had a monomial degeneration of the tensor on the left, it would also, into an independent tensor, it would also give that, like that same monomial degeneration would also degenerate each of these terms on the right to an independent tensor and give upper bounds on I sub md of all those terms. So it's less than or equal to the sum over each component of I sub md. For each of those, we have the bound q plus 2 to the 2n over 3. So overall, since there's 3 to the end of them, we get this upper bound on I sub md. And just rearranging it shows it's at most q plus 2 to the 1 minus delta, where delta is this thing which is getting bigger as q gets larger, like I promised it would. Yeah, so it's pretty simple, and that's actually the whole proof. Okay. Yeah, so just to conclude, so I think maybe these lower bounds, you might think of them as some negative type of result, like, oh, maybe it's hard or impossible to prove omega is equals 2 now. But I think you can actually view them in a positive light also. It's like we give some nice combinatorial properties like this probability distribution lemma that nice tensors that are easier or better to analyze would have. So maybe this can help narrow in on tensors that could help us get a bit better bounds on omega. Yeah, so I think it would be really nice to, well, I guess maybe Virginia alluded to this earlier, but I think we more or less know how to extend these results to the universal method too. But more generally, more lower bound techniques and figuring out exactly what types of approaches could improve omega and what types couldn't would be really exciting. Yeah, thanks.
So for the group tensor, you're using some version of the polynomial method, is it? Or how do you?
Yeah. So the most succinct way to describe it, I guess, is you can show that if the tensor or a big power of the tensor has a monomial degeneration to a big independent tensor, that means the group has, or a power of the group has big tricolored sum-free sets. And for instance, using the polynomial method, they show that these things can't exist. Yeah, that's the idea. Yeah.
So if I understand correctly, the difference between the universal method and the galactic method is the ability to change bases.
Yeah, that's right. Yeah. That's why it's hard to, like, I guess we made lots of arguments about the number of different variables, and when you can do these linear combinations to bigger sets of variables, it's a bit harder to argue about these types of things.
Other questions? Okay, so let's thank Josh.